All right, let's talk about something pretty wild in the world of engineering. A wastewater system that, well, it basically eats itself. It's a fascinating way to solve a huge problem, so let's get into it. Okay, so if you've ever dealt with wastewater treatment, you know the biggest headache, right? It's that stuff left at the end, the sludge. It's messy, it's expensive to get rid of, it's just a constant problem. But what if you could design a system where it just kinda vanishes?
So, to really get why this self-eating system is so brilliant, we first have to talk about the main villain in this whole story. And that is, you guessed it, the sludge problem.
You see, in most wastewater plants, when you clean the water, you're left with this huge amount of, well, sludge. And getting rid of it, it's a real pain. It's not just about dumping it somewhere. You have to treat it, handle it, transport it, and all of that costs a ton of money and burns a lot of energy.
Okay, so we have our villain. Now, let's bring in the hero of our story, extended aeration, and its secret weapon, a really clever strategy that we can think of as the starvation diet. The whole point is to stop that sludge from ever becoming a big problem in the first place.
So here's the big idea, right? In any system, you've got this tiny microbial workforce doing the dirty work of cleaning the water. Now, a normal system, it's like an all-you-can-eat buffet. The microbes gorge themselves on pollutants, they multiply like crazy, and you get tons of sludge. But extended aeration, it's different. It puts those little guys on a super strict diet. So strict, in fact, that they get so hungry, they start eating each other to survive. And this is how that diet actually works in practice. I love this analogy. A conventional system is like a microwave. It's super fast. But extended aeration, that's a slow cooker. And you can see it in the numbers. Look at the solids retention time, the SRT. We're talking about keeping the microbes in the system for 20, maybe 30 days instead of just a handful. And check out the food-to-microorganism ratio. It's incredibly low. That's the starvation part we were talking about. And all this means the water itself has to hang out in the tank way longer. That's the hydraulic retention time, sometimes for a day and a half. So there's a cool scientific name for this whole process: endogenous respiration. Yeah, it sounds complicated, but it's really just a fancy way of saying what happens when cells run out of food. They don't just give up and die. Nope, they start cannibalizing their own internal bits for energy. And in this system, we're doing that on purpose. We're forcing this state to make the sludge problem just solve itself. The microbes are literally eating their own population down to a manageable size. Okay, so that's the theory, right? Starve the microbes, make them eat themselves, less sludge. Simple enough. But what does this actually look like in a real-world treatment plant? Let's take a look. The whole setup is actually beautiful in its simplicity. So first, the incoming wastewater gets screened, to get rid of any big stuff. From there, it goes straight into this giant aeration tank. This is our slow cooker. The water and the microbes hang out in here for a long, long time. We're talking 18 to 36 hours. After that, it moves on to a clarifier, which lets all those microbes settle down to the bottom. And here's the key. Almost all of that settled sludge gets sent right back to the beginning of the aeration tank to get back to work. Almost none of it actually leaves the system. But hold on a second. Did you notice something that's missing? If you're familiar with treatment plants, you might be looking for the primary clarifier. And it's not there. That's not a mistake, that is the whole point. By skipping that step and sending all that raw organic food straight into the aeration tank, the system perfectly controls the diet. It's just enough food to keep things ticking along, but not enough for the microbes to feast and multiply out of control. It's a brilliant bit of mechanical simplicity that's only possible because of the biological strategy. Now this all sounds pretty amazing, right? A system that eats its own waste. But you know how it is with engineering. There's no free lunch. There are always trade-offs. So let's break down the pros and cons, the payoff versus the price. Okay, let's start with the good stuff, the payoff. And it's a big one. First off, you get way less sludge. I mean, that was the whole goal, and it delivers. Plus, the system is incredibly stable. That massive tank can handle shocks and changes in the wastewater flow without missing a beat. It's also really good at removing nitrogen, which is a huge bonus. And it's mechanically simpler. And because air is constantly being pumped through it, you don't really have to worry about bad smells. All right, but what's the price you have to pay for all those benefits? Well, for one, those giant tanks aren't cheap. So your upfront construction cost is going to be higher. And the big one? Energy. You have to run those air blowers pretty much constantly to keep everything mixed and aerated, and that uses a lot of power. It's really the classic engineering trade-off, isn't it? You're saving money on sludge handling, but you're spending more on your electricity bill. So, when you weigh those pros and cons, the low sludge versus the high energy, you start to see where this system fits in perfectly. It's not for everyone, but it has carved out a perfect niche for itself where its strengths are exactly what's needed.
And this is exactly where it shines. We're talking about smaller scale applications. Think about a school out in the country, or a new residential subdivision, maybe a little commercial park, or even a small town. In these places, you might not have a full-time, highly specialized operator on site 24/7. So for them, having a system that's super stable, simple to run, and doesn't produce a mountain of sludge to deal with, well, that's way more important than saving a bit on the energy bill.
So, at the end of the day, the extended aeration system is a total workhorse. It's a robust solution that tackles that massive sludge problem by making a very clear trade. It gives up energy efficiency for rock-solid simplicity and stability. And that really leaves us with a big question to think about, doesn't it? As our communities grow and change, how are we going to balance these two critical needs? The need for simple, reliable infrastructure on one hand, and the absolute necessity of energy efficiency on the other. Finding that balance, well, that's going to be one of the key challenges for building a sustainable future.